So I tell people, I tell Jambites, when you see a question, the very first thing you have to know is that question is coming from which topic. When you see a question, I don't know the topic the question is coming out from. You basically cannot approach or solve that kind of question. So when you see a question, you have to know, is this question coming from acid, base, and salt? Is it coming from gases? Is it organic chemistry? Is it hydrogen? You have to identify the source of the question. So when you know the topic that question is coming out from, then you can now streamline your line of thought. Okay, so now this question is giving us a number of parameters. We have the volume being given as what? 10 dm3. Okay, we have the pressure being given as 4 atmosphere, and then we also have a temperature there, which is 273 Kelvin, 273 degrees Celsius. Okay, now we are asked to get the number of moles of the gas. So how do we solve this? We are also given gas molar volume. We are also giving gas molar volume of gas at STP. We are giving molar volume of gas at STP to be to be 22.4 gm3. So there are two ways of solving this problem. The first method, which is going to be method 1, is by assuming that the gas is ideal. When you assume that the gas is ideal, what do you mean? You are going to be applying the ideal gas equation, which is PV equals to what? nRT. So what you are looking for is the number of moles. So when you make number of moles subject of formula, that will be PV over what? RT. That will be PV over RT. Okay? So you can now see that you have your pressure, which is 4 atmosphere, multiplied by your volume, which is 10 dm3, divided by, now this R here is what we call universal gas constant. It's what we call what? Universal gas constant. The R there is the universal gas constant. Okay? So if R is universal gas constant, now what is the value of the universal gas constant? The value of the universal gas constant is 0.0821 atmosphere liter per mole per Kelvin. Atmosphere liter per mole per Kelvin. Also, the R is also 8.314 joule per mole per Kelvin. This is the SI unit. Okay. Now, when do you use the 0.0821? And when do you use 8.314? It all depends on the unit of the parameters, the unit of the pressure, the unit of the volume, and the temperature. So, well, the question we are actually using might have some typographical error, maybe. Okay, so you just get the concept. That temperature, that 273 degrees Celsius, I'm seeing it as what's it called? Okay, let's say 273 degrees Celsius. When you convert this will now be what? Convert this to Kelvin, that will be 273 plus 273. And when you add 273 plus 273, what do you have? That will give you 273 plus 273. That will give you 500 and what? 546 Kelvin. So your temperature is 546 Kelvin, and the R is 0.0821 atmosphere liter per mole per Kelvin. So you can now complete these answers, and then you get your number of moles. So what you see is that the ATM here will cancel the ATM here. This liter is the same as dm cube, so it cancels out. Kelvin cancels out Kelvin, so you're only left with what? You're only left with moles. Am I making any sense? So when you see question, the one you are going to be giving your exam is not going to be as complex as this. So when you are giving volume, pressure, temperature, and then you want to get number of moles, they can actually change the concept of the problem. So, but what is most important is that PV equals to what? nRT. So you know that PV equals to, so any of the parameter that was given or that is unknown, provided the others are given, the R will also be given in the question. They will give you the R in the question, the universal gas constant. They will give you the question. Okay. So, but what is most important is understand the logic behind the problem. Now, another style of solving this problem is by using the gas molar volume. Now, how do we use this gas molar volume? This molar volume of gas, otherwise called gas molar volume, what it means is that for every 1 mole of any gas, it is going to occupy a volume of 22.4 dm cube at STP. For every 1 mole of any gas, it is going to occupy a volume of 22.4 dm cube at what? At STP. It's going to occupy a volume of 22.4 dm cube at STP. Now, we are given that this is the volume of the gas at this pressure, at this temperature. Now, what does the STP means? Take note. The standard temperature and pressure means standard temperature of 273 Kelvin and standard pressure of what? 1 atm. Now, you cannot compare this and this together. You know why? Normally, what we want to do is that we'll say X mole is that, what we are looking for. How many X mole do you have in a certain volume? But we cannot use this volume because the condition of this volume is at a pressure of 4 atmosphere, and the that is not even standard what? Temperature. Are you getting my point? But in a very, very simplified question, you are going to give you, like I say, 1 mole of a gas. You can say a certain, how many moles of a gas? Okay, let me just frame this question this way. What is volume of a certain gas? What is volume of, let's say, 3 moles of a gas at STP? Okay, in that case now they're asking you for volume. When you know the number of what moles, all you do is multiply the number of moles by the standard gas molar volume. So solving this question this way is going to be practically impossible. It's not practically impossible, but it's going to be difficult because we need to convert this volume at these conditions to volume at this condition. And for you to now do that, you might now need to start doing P1 V1 over T1 equals to P2 V2 over T2, which is actually a lot of stress. Okay, so this is still the best approach for the problem. But above all, in your exam, you have to see something that is difficult. Okay, so according to Charles' law, the volume of gas becomes zero at what? Now, according to Charles' law states that the volume of a given mass of a gas is directly proportional to the absolute temperature. A lot of people just say it's directly proportional to temperature. It is not temperature. The law did not say that volume is directly proportional to temperature. It is directly proportional to absolute temperature. So what is now the difference between temperature and absolute temperature? Absolute temperature means temperature of a gas when it is measured in Kelvin. Volume measured in Kelvin, temperature measured in Kelvin rather, is the temperature in Celsius plus what? Plus 273. Okay. Now, Charles' law now gave us a graph. Which is that this is a graph. This is a graph of volume in degrees Celsius, and this is a graph of temperature. Volume in maybe liter or whatsoever, temperature in degrees Celsius. So we realize that the graph cuts the negative x-axis at minus 273 Celsius. Now, this temperature, that is the temperature where a gas becomes the volume of the gas becomes zero. At this temperature, you can see this is when the volume of the gas becomes zero. So that temperature when the volume of the gas becomes zero is minus 273 what? Degrees Celsius. That's the answer. Okay, now let's go. Question 3. So take note of that. Take note of this graph. So this is an illustration of Charles' law. volume in whatever unit, whether liter or dm cube, against temperature, it cuts the negative x-axis on this side at a value of minus 273. That is why when I want to convert the Celsius to the Kelvin, what we always do is that we are adding what? 273. Because every Celsius, for we to convert the Celsius to Kelvin, we need to add that correction factor, that plus 273. The next question. A substance that is used in ripening of fruit is dash. Now, the correct answer in that question is ethene. Ethene is what is used in ripening of fruit, not ethane, and not propane, and not methane, and not butane. The correct answer there is ethene. Okay? Now, let's go. Question 4. Now, this is just a use of alkene. When you read your alkanes, you read your alkanes, your organic chemistry, you see that ethene is used in ripening of what? It's used in ripening of fruit. Another question there is the sulfide which is insoluble in dilute HCl. Now, how do we know the sulfide that is insoluble in dilute HCl? Now, when you react those sulfide, say FeS plus HCl to give you FeCl2 plus H2S, and then we also have CuS plus HCl to give you CuCl2 plus H2S. Okay. Zinc sulfide plus HCl to give you zinc chloride plus H2S, and Na2S plus HCl to give you NaCl plus H2S. Now the question is, which of these is actually insoluble? Now, the one that is insoluble, the sulfide that is insoluble in dilute hydrochloric acid, so this is actually a form of inorganic chemistry. And one thing about inorganic chemistry is that you actually need to familiarize yourself with it to know it. Okay? You actually need to familiarize yourself to know it. It is FeS, iron sulfide. When you dissolve iron sulfide in HCl, it is actually what? It gives you an insoluble observation, like an insoluble precipitate. Okay? So the correct answer there is iron what? Iron sulfide. So you actually know this when you read your inorganic chemistry. The pH of sodium hydroxide, you are given 0.001 mole per dm cube of sodium hydroxide. So this is the concentration of the sodium hydroxide, and when you get the pH. So we go. Now what you do is, your sodium hydroxide is a base. When it ionizes, it gives you what? Na plus and what? OH minus. Look at this. This is 1:1:1. What this means is that if the concentration of this is 0.01, this concentration of the OH minus will also be what? 0.001. Because they are both 1:1. So that means that from this 0.01 mole per dm cube of sodium hydroxide, what you are getting from here is concentration of what? OH minus. What you are getting from here is concentration of OH minus to be 0.001. If this are something like copper hydroxide, when you ionize this, or calcium hydroxide, this will give you calcium 2 plus and 2 OH minus. In this case now, this is 1:1:2, which means that if I give you this to be 0.01, for you to get the concentration of the OH minus, what are you going to do? You're going to multiply by what? You're going to multiply by 2, because that means that for every one of this, it gives out 2 of this. So for every 0.01 of this, it gives out 2 times 0.01 of this. But in the case of sodium hydroxide, when it ionizes, it gives you 1:1. So you have that. Okay? So 0.001 mole per what? Per dm cube. Now, when you now know the concentration of the OH minus, this cannot give you pH. That's what, most times when students say a question like this, calculate pH, they just put this value, they just put it in the formula. No. I'm giving you sodium hydroxide. Sodium hydroxide can only give you OH minus. So, knowing concentration of OH minus cannot give you pH. what it can give you is what? POH. I get my point. What it can give you is POH. So what's the formula for POH? POH, the POH, just like pH, is minus log 10 what? OH what? OH minus. So what do you have? Minus log 10, 0.001. And for those that know mathematics, they know that this 0.001 is 1, 2, 3. It's actually 10 raised by what? Minus 3. And for those that know mathematics, they know that this is minus 3 log 10, 10. What is log 10, 10? 1. Everything here is what? 3. You are going to see this option in the question. If you look at that, you're actually going to see this option. This option is going to be in the question. Because this is what a lot of students will do. They will just put this value in that formula. Because don't forget, the formula of pH and formula of POH, they are not anyway different. The only thing is just that pH depends on concentration of H plus. POH depends on concentration of OH minus. The substance you are giving is sodium hydroxide. It contains OH. So that means that what you can get from here is concentration of OH minus. And when you can get concentration of OH minus, what this can give you is what? POH. It cannot give you pH. So now that I don't know concentration of H plus, that's why I cannot get pH. Now that I know the POH, you now recall that pH plus POH equals to what? 14. Your pH now be what? 14 minus POH, which is what? 14 minus 3. That's what? 11. Am I making sense? So in that question, you're actually going to see this 3. You're actually going to see 11 too. Yes. That option B, what they intended by that 13 is 3. Okay? It's 3. So when students solve, when you see that 3, when you are solving an objective question and you see your answer, you're always happy. You're always happy that like you are correct. That's the problem with Jamb. When you are doing objective and you are solving calculation, the problem might actually be a two-stage problem. The problem, you getting 3 is just like stage 1 of the problem. Am I making sense? It's not like stage 1. But out of your fear, your anxiety, and your anxiety and composure, you just 3. You quickly pick it and then you say you have killed Jamb. Meanwhile, Jamb is one that has killed you. So you have to make sure that you understand what you are doing. You understand what the problem is saying. What type of bonding is present in that? So we have this complex ion, CuNH3, 4, 2+. Now, what type of bonding is this? The bond that is present here is what we call dative bonding. It's what called what? Dative bonding, otherwise called what? Coordinate covalent bond. Now, how do I know this? Copper is transition metal. Yes, copper is a transition metal. Copper is a transition metals, and transition metals have something. They have a serious. Okay, so now this is transition metal, copper. It is actually we call it central transition metal. It will be in the middle. This is the ammonia NH3. There are 4 of them. Okay, so we have the ammonia in that manner surrounding it. So there's actually a bond from here to here. There's a bond from here to here. There's a bond from here to here. There's a bond from here to here. Now, it is actually this bond, this arrow that you're seeing is actually a representation for the dative bonding. It is just your normal covalent bonding. Don't forget, the basis of covalent bonding is what? There is sharing of what? Electron. But what is the difference between your normal covalent bonding and coordinate covalent? The difference is not far-fetched. The difference is that in normal, ordinary covalent bonding, because when you say you are sharing something, it's like you have a bond between chlorine and another chlorine. This bond you are seeing here now, one of the electron is coming from this chlorine, the other electron is coming from this other chlorine. So it is like a kind of mutualism. You are bringing, I'm also bringing. That is ordinary covalent. You bring, I bring. What you are bringing is electron. You bring electron, I also bring electron. We are contributing, we are both contributing to the electron that is being shared. But in coordinate covalent, I'm the only one bringing. You are not bringing. It is the ammonia. The ammonia has a low pair of electron here. It is the ammonia that is bringing the electron that is being shared. Copper is not bringing anything. Am I making a sense? In actual sense, what this is actually for everything 2 plus. Am I making a sense? So the copper is not bringing any electron. It is only the ammonia that is bringing the electron that is being shared. So in that type of bonding, where only one of the participating species, in that type of covalent bonding, where only one of the participating species is bringing the electron that is being shared, you call that coordinate what? Covalent bonding. Otherwise called what? Dative bond. Another example of where you see dative bond is this. That dative bond is something like this. Water combining with H plus to give you what? H3O plus. And the H plus to form a bond with this guy to now give you what? This will now look like this. To now be what? H, O, dative bond H. And then everything what? Plus. So we also have what? Dative bond in here. So that's another example of where you have what? Dative bond. So dative bond is just a special form of your coordinate covalent bond. Another question: which of the following is an example of so the answer there is coordinate covalent bonding. Which of the following is an example of a chemical change? When you dissolution of salt in water, when you dissolve salt in water, it's not a chemical change. It is just what? A physical what? Is a physical change. Okay, you know physical change and chemical change. Physical change can be reversible. Chemical change cannot be what? Cannot be reversible. When I pour salt in water, I can actually reverse it. Okay, I can reverse it. I can get back my salt if I eat. Okay, rusting of iron. Rusting of iron is a chemical process. Rusting of iron is a chemical process, popularly called what? Corrosion. Popularly called what? Corrosion. So that is not a physical change. That is actually what? A chemical change, because you cannot reverse when iron is rusted. Because that rust, this is actually what is happening there. Please take note. For corrosion to take place, you can see this question in Jamb. In fact, it's coming out. You're going to see it. For corrosion to take place, 2 things are necessary. The first is water. There was water vapor. And then the second is what? Oxygen. So most times, when you see an iron rod being coated or plated, or coated with paint or something, what they are trying to do is just to decrease the rate of what? The corrosion, the exposure. Because the more exposed the iron is to water, rain will fall now. Oxygen is everywhere. The more it gets in contact with oxygen and water, the more that reaction occurs, and then rusting occurs. So this is actually what is happening. Iron is combining with oxygen with a certain amount of H2O to give you an ore, to give you an oxide. Now, if you look at this oxide is Fe3 plus. Now, you know that this Fe3 plus has a color of what? Brown. That is why your rust, when iron is rust, when you see a rusted iron, it will have that brownish color. That is, remember, that brownish color is what? This oxide that has been formed. It is this oxide, Fe3O4.XH2O, that has been formed on that what? On that surface. So that is a chemical change. It's not a physical change. You cannot reverse it. It's not. You can only try to limit the extent of the pollution. And what is to limit the extent of pollution? What are people need to limit the extent of pollution? Number one is to try to print whatever material. Number two is what? Electroplating. You try to electroplate something that does not easily work for it. That's why you have what's called galvanized iron or galvanized. Okay, so let's do that. So that's the melting of iron. Melting of iron is a physical process. When ice melts the water, it's a physical process. Melting. I can also go from water, liquid water back to ice. That is solidification. Okay. Separation of a mixture by distillation is a physical process. Separation of a mixture by distillation is a physical process. In that case, what you are just using is that you're only applying heat. Okay, you have a mixture of water and ethanol. Ethanol is soluble in water. When you have a mixture of water and ethanol, to separate them, you use what? Distillation. Mind you, another jam question there. They can ask you, on what principle does distillation works on? Distillation works on principle of what? Difference in what? Boiling point. It is the difference in boiling point. You can separate ethanol, ogogoro, and water by distillation. Why? Because ethanol has a boiling point of 78. Water has a boiling point of what? 100. So that difference in the boiling point is what is responsible. That is why when you now have the mixture, you have a mixture of both of them. You have a mixture of both of them in a jar. Okay. Then you apply heat. When you apply sufficient amount of heat, as the temperature is rising, what happens is that once you get to the boiling point of this what? Ethanol 78, the ethanol content of this, what happens? It vaporizes. And once it vaporizes, what's the next thing? There will now be something here called what? A condenser. So that condenser will now turn the vapor, the ethanol vapor, back to the what? Back to liquid ethanol. And it is also this principle that is used in separation of fractions of crude oil. So take note of that. Fractions of crude oil. When you get crude oil, what Dangote is doing now, you get crude oil. Crude oil, like the word implies, crude. You cannot use it like that. It is useless unless you undergo a process called what? Refining. Now refining is employing what? The major process in your refining is fractional what? Distillation. Now, what is the between distillation and fractional distillation? In fractional distillation, you are telling me that the crude, when you subject the crude to the distillation tower, it gives you more than one product. So you have, when you subject crude oil to distillation tower, you have what? Petroleum gas. You have the gases coming out. That's where you get your liquid petroleum gas, LPG, LNGs, and the like. You have your what? Your petrol, gasoline. You have your what? Your kerosene. Okay? You have your what? Your diesel oil. And then you have your bitumen. You have a number of things. All these things are so the operating principle of the fractional distillation is what? Is difference in what? Point. So the boiling point of this, boiling point of this, and take note, the ones at the top are said to be what? Light. The ones at the bottom, which like bitumen and whatever residue, those ones are said to be what? Heavy. So it is the lighter ones that have low boiling point that comes out first. It is the ethanol that has low boiling point that comes out first. It comes out first in that mixture. When it comes out, because it has gotten to the boiling point, it comes out as vapor. So when it comes out as vapor, then you now put your condenser. The condenser will now convert the vapor ethanol to liquid what? Ethanol. So in that way, you have successfully separated ethanol and what? Water. So take note, a mixture of ethanol and water can be separated by what? Distillation, because of what? Their difference in what? In boiling point. Your crude oil is also separated in fractional in the refinery based on the principle of what? Fractional what? Distillation. Okay, so that is that about that. So let's go. To what temperature must a gas at 273 K be heated in order to double its volume and pressure? Very simple. To what temperature do I need to heat a gas for the pressure and volume to be doubled? So what would that? Just a gas law question. So initially we said P1, B1, T1. Now we want to double the pressure. That will now be 2P1. We also want to double the volume. That would be 2V1. Am I making a sense? Okay. What would not be the new temperature? So what you do here is just P1V1 over T1 equals to what? P2V2 over what? T2. So what do we have? P1V1 over T1. What's our P2? We are doubling the initial pressure, 2P1. What's our V2? We are doubling the initial volume, 2V1 over T2. P1 cancel out P1, P1 cancel out V1. So what do we have? 1 over T1 equals to 2 times 2, 4 over T2. So what do we have? T2, when you cross multiply, is what? 4 what? 41. That means that it is 41. And what's the initial temperature? The initial temperature is actually 273. So 4 times 273 will be the answer, which I think is 1092. Yeah, 4 times 273. 4 times 273 is 1092. So that's option D. Okay. Now the next question there. According to the kinetic theory of gas, according to kinetic theory, an increase in temperature causes the kinetic energy to do what? According to kinetic theory stated a number of things. What are the postulates of kinetic theory? The first thing is that now, when we say kinetic theory, we can talk about kinetic theory of matter. We can talk about kinetic theory of gas. We can talk about kinetic theory of matter. We can talk about kinetic theory of gas. Okay. So now, what kinetic theory is saying is that, for this question, when you increase temperature, what happens to kinetic energy? It increases. What is kinetic energy? Energy due to what? Motion. When you are increasing temperature of something, when you are increasing temperature, what you realize is that what? You are increasing the kinetic energy. It's just like you have a pot, you put that pot of water. The temperature keeps on rising. Wow, you now see some particles bubbling. You see some particles bubbling. If the temperature continue to rise and rise and rise and rise up till you get to the boiling point, what happens? The particles will get enough sufficient energy so that some of them will even be able to escape. So when you increase temperature, what will happen is that you are increasing what? Kinetic energy. Okay. Now, next question. A basic postulate. Okay. Before that, an element used in production of matches is dash. The element that is used in production of matches is what? Is sulfur. Yeah, is sulfur. We actually need to go and read on non-metals. When you read non-metals, all these things you are going to get the information. Okay. Sulfur. That's the element you have there. Hospital.